Okay, we're back with another video. This time we're going to look at question number 6 of assignment C. And essentially what we have here is an opportunity to take advantage of the pigeonhole principle. So we assume n is even, right? That's in essence the pigeonhole principle, and the idea here is that for n sufficiently large, an even n and an odd n are essentially the same number. So it makes counting just a little bit easier. And I'll take advantage of that pretty much throughout the problem to show that we can get omega of n squared and omega of n for the respective problems. So let me just try to find, so here are the questions. So we have that square mesh network, and now we're asked some things about that square mesh network. So part 1, we show that in total at least omega of n squared packets have to pass through the nodes along the line L. So I'm just going to freehand draw this to be a little bit faster, but essentially we have a square mesh network. Okay, in this corner we have index 0, 0, and in this corner we have index n, n. And we draw a line across the center. And this line is L, and L has, or L contains n nodes. So there's n nodes in L. Okay. So part 1, and essentially towards the end of this problem, we're told that we have each of the n over 2 nodes in the bottom half, 0, 1 to n over 2 minus 1 to 1. So 0 column 1, 1 column 1. So not the edge, right? Not this very edge node, but just one row over. These nodes here will communicate to all the n over 2 plus 2, starting here, n over 2 plus 2 to n over 2 plus 2n. So all of these nodes here. Oh, wait a minute. N over 2 plus 1 by n. Yeah, so they're all in column n. So they're all over here. It's this top half of this column, all of these nodes. So all the nodes here have to communicate to all the nodes there. Yeah. Alright, so essentially we have a bunch of shortest paths. That's another part of the problem. We say suppose that each of those nodes at the bottom half of the grid route packets, 1 packet per node, to each of the nodes at the top half of the grid using any shortest path. So, in other words, none of these packets are going to go this way or this way. They're not going to take a longer than the shortest path. So we're all going to be using, or rather all of these nodes will be using one of, if there are more than one of the minimum eccentricities to the node that it wants to target with a packet. The idea there is that we're saying that the traffic is evenly distributed along this line L, along all the nodes in this line L. Okay, that's the idea of the shortest path, right? That's what it's communicating. Essentially, if I have a node right here, it won't see all of the traffic because it's going to be not the shortest path for all of these. So let's look at part 1, and part 1 should be pretty simple. We're going to ask for the order of the messages. So we say that the message complexity m is going to be equal to all the packets that go across all of these edges, right? So if I look at any given edge that exits one of these nodes, it's going to see 1, 2, 3, 4, 5, all the way to n packets leaving. So each one of these n nodes will send n messages, which means that the complexity will be n squared. Now in the bottom half we have essentially n over 2 nodes, and in the top half we have essentially n over 2 nodes. Okay, technically, more specifically, we have n over 2, or n minus 1 over 2, and n over 2, n minus 1? Over 2, yeah, and n minus 1 over 2 here. No, n over 2 minus 1 because there's one node here, and n over 2 minus 1 here, but we can essentially invoke the pigeonhole principle again, right? Because that number should still be sufficiently large that it might as well be n over 2, and this might as well be n over 2, right? Because if n is sufficiently large, n over 2 is sufficiently large, and thus n over 2 minus 1 is sufficiently close to n over 2. So I'll make this slight approximation in my counting to make an easier message complexity. It's not a huge deal, I don't have to do it, but I can, so I will. So why not? So essentially I have n over 2 senders, and each of those n over 2 senders sends n over 2 messages, which gives me a message complexity of n over 2 squared, right, which gives me n squared over 4 messages, which obviously from this shows that we have the lower bound of n squared, right? The lower bound is on the order of n squared. So that's question 1 done. Now part 2 for this question asks, show that at least omega of n packets have to pass through a node in the line L1. Right, so we're showing now that in part 2 that the lower bound, the omega of n, will pass through here. Well, we said it's shortest paths, and by merit of it being shortest paths, all the packets are evenly distributed across this line, which means that none of them will have more and none will have less. So essentially what I can say is that the message complexity for this line will look like n over 2 squared divided by all of the nodes in the line, which would be that. So then again I have 1 over 4n n squared, and that leaves me with 1 over 4n, right? So okay, that shows that my lower bound here is on the omega of n. Alright, so now part 3. Well, now all n minus 1 nodes in L are failing, right? They're all failed, which means I have exactly one node that everything can pass over, right? We say now assume all but one of the nodes on the horizontal line L are faulty and cannot route packets. So now we have only this one node that can possibly take a packet. So suddenly what happens here is that the shortest path, every single shortest path that is possible from this lower half to the top half of the network must go through this node. So now for 3, we say ML, and I'm going to put an F to represent the line is faulty, is this n over 2 squared divided by 1, which is now back to the m that we calculated in the first part of the problem. So this is just m, which then shows me that this is now on the lower bound omega of n squared. So there's really not much more to this problem. I think the difficult part in this problem is understanding how to view this statement and that statement, right? How do we divide this sender and receiver portion of the mesh, and then from there we can compute the message complexity that we actually have. So that's essentially all there is to question 6, and I will see you in the next video for question 7.